Hi, my name is Valentina Pastrana, and I'm going to be showing how to solve the following complex power problem. So the circuit shown is in steady state. The first thing I'm going to do is I'm going to rewrite all the complex power for all the loads. So it's going to be step 1. So for S1, we're already told that it's going to be 1500 with an angle of 37 degrees. It's going to be in volt amps. Now for source 2, we know that the complex power follows the equation S is equal to P plus JQ. Now this is going to be, P is going to be the real power and Q is going to be reactive power. We know that this is going to be the real power because it's in watts, and then we can use the leading power factor to solve for the reactive power. So the way we're going to do that is we know that the power factor is equal to cosine theta, and using this triangle, we also know that cosine theta is equal to P over S. So we know power factor is equal to P over S. Now this is what we're trying to solve for right now. So I'm going to rewrite the equation. So it's going to be S is equal to P over the power factor. So it's going to be 750 watts that we got from the problem statement over 0.63. And that's going to give me 1190. And now we just have to find the angle, because this is the format that I'm trying to get it into. So now I have to find the angle. I can also use this equation again to find for this angle. So we know theta is going to be cosine inverse of the power factor. So this is going to need to be equal to cosine inverse of 0.63, and that's going to give me a negative 50.9 degrees. So S2 is going to equal 1190 with an angle of negative 50.9 degrees volt amps. I'm going to highlight these real quick. This is going to be S for load 1 and S for load 2. Now for load 3 and 4, we're basically already given the power, so it's going to be S3 is equal to 1270 minus J560 volt amps. And for source, for the load 4, we know it absorbs. It's going to be our P right here. That's going to be the real one. And this is going to be the reactive. And because it delivers, this is going to be negative. So it's going to be S4 is equal to 1370 minus J540 volt amps. And again, we know that this is negative because the problem statement says delivers. Now for part A, we are asked to find the reactive power delivered by the source. Now we know that the total power for the circuit is going to equal to the sum of all the loads. So we can use the equation S total is equal to S1 plus S2 plus S3 plus S4. So that's going to be 1500 with the angle of 37 volt amps plus 1190 angle negative 50.9 degrees volt amps plus 1270 minus J560 volt amps plus S4, which is 1370 minus J540 volt amps. And I'm just going to plug all of this into my calculator. And from there, I get S total is equal to 4588.4 minus J -1120 volt amps. Now this is going to be the complex power equation for the entire circuit, but we're specifically asked for reactive power. So once again, we know that S is equal to P plus JQ, and we know that Q is going to be our reactive power. So this right here is going to be the reactive power, but this is the reactive power absorbed. So this is going to be Q ABS is equal to -1120 volt amps. And the problem asked for delivered. So we're just going to flip the sign. So Q del is equal to 1120 VA, and this is going to be the answer for part A. And then for part B, we're asked to find Ix of t. So for part B, I'm going to use the equation S is equal to VRMS times IRMS conjugates. Now we're giving the VRMS, well no, we're giving Vs of t, and we can use this to find VRMS. And then we also need to know that we're giving this in sine. And to convert this cosine, we're going to have to subtract 90 from this angle. So VRMS is going to equal 370 over the square root of 2 with an angle -12 minus 90. And I got this from the equation. Use equation VRMS is equal to V over square root of 2. And then I'm going to rewrite this equation to isolate IRMS conjugate is equal to S total over VRMS. So this is going to be able form minus J1120 over 370 over the square root of 2, angle -102. And I'm just going to plug that into my calculator again. And we get the conjugate is equal to 18. Sorry, this is IXRMS. 0.03 with an angle 94.28. Now, since this is the conjugate and we need just regular RMS, that means I'm going to change this sign of the angle. So our IXRMS is going to be 18.03, angle -94.28. Now to convert IXRMS to the time domain, we can use this same equation. So that's going to be Ix of t is equal to the square root of 2 times IXRMS. So it's going to be square root of 2 times 18.03, angle -4.28 degrees. And I'm going to use this number right here to write the actual equation. So that's going to be Ix of t is equal to 18.03 times square root of 2 cosine 500t minus 94.3 degrees. So this is going to be the answer for part B. And now for part C, we're asked to find the equivalent impedance of the combination of the 4 loads. And there we can use equation VRMS is equal to IRMS times C. This is going to be the impedance. And then we just rearrange the equation. C is equal to VRMS over Ix RMS. And then these two values we already solved for, so that's just going to be 370 over the square root of 2, angle negative 102 degrees, over 18.03, angle negative 94, and this is going to be 14.4, angle negative 13.72 degrees. And then this is going to be the answer for part C. And that's the end of the problem.